Welcome back to our study on probability distributions. Today we're talking about continuous distributions and area. And we're going to work a lot with this guy, Z. He's sort of the king of statistics, and I think you'll see why. As a review, a probability distribution is a table or an equation that links each outcome of a statistical experiment with its probability, so you can see both. The outcome of a probability experiment is either a count or a measure. The count would create a discrete distribution, and a measure would create a continuous distribution. We call these counts or measures random variables. So for continuous probability distributions, they show outcomes and probabilities for measurable random variables. The most famous of these is what we call the normal distribution. In the normal distribution, the mean, median, and mode are all equal. The total area under the curve is equal to 1, and the curve is symmetric about the mean. They can have a lot of differences too, though. Let me show you what I mean. Here's 3 normal distributions, and these normal distributions have different means, but they have the same standard deviations. These normal distributions have the same means, but different standard deviations. And then these normal distributions have different means and different standard deviations. Here's the thing. There are an infinite number of normal distributions, each with its own mean and standard deviation, and that's too many. So we use the standard normal distribution with a mean of 0 and a standard deviation of 1. Then we use z-scores, which are sort of like translators from any of those infinite number of distributions to the standard normal distribution. We use z-scores to find the area under the curve, which tells us the probability of an event occurring. Let's do a quick review on z-scores. We looked at this before when we were talking about measures of position. And measures of position are a starting point for us today. The SAT is an exam used by colleges and universities, as you know, to evaluate undergraduate applicants. The test scores are normally distributed. In a recent year, the mean test score was 1059 with a standard deviation of 125. The test scores of 4 students selected at random are 996, 1287, 1408, and 815. So we're going to find the value of each. We're going to plot them and label them on the normal curve. Then we'll circle any values that would be considered unusual. First thing we need to do is remember what our z formula is, x minus mu divided by sigma. We'll draw ourselves a curve and mark mu right in the middle of the curve. Now we can start finding some z-scores. So for the first one, take 996 minus the mean of 1059, divide that by the standard deviation of 125, and we get a z-score of negative 0.504. So we can plot that below the mean on our normal distribution curve. The next one is 1287, so 1287 minus 1059 divided by 125 gives us a z-score of 1.8, so that's above the mean. Next is 1408, same thing, 1408 minus 1059 divided by 125 gives us a z-score of 2.792, far above the mean. And the last one, 815, gives us a z-score of negative 1.952. The last thing we need to do is circle any values that would be considered unusual. When you're working with the normal distribution, unusual values are 2 standard deviations above or below the mean. So that gives us 2.792 as an unusual value, or the score of 1408. Now we're going to go one step further and find the area under the curve, not just the position. Let me show you how this works. Find the area under the curve between z equals negative 1.5 and z equals 1.5. So we want to find this area in between those two values. So you need to pull out your calculator, and on the T84, you're going to hit second vars, which is a distribution button, and we're going to go down to normal CDF. On the TI-84 Plus, it looks like this, normal distribution, go down 2 to hit normal CDF. And then you're going to put in the lower bound of negative 1.5 and the upper bound of 1.5. Then just click through the mu equals 0, sigma equals 1. That's telling you that we're working on the standard normal distribution. And hit enter. And this is what you should see. Now, if you're working with an older version of the calculator, you just put in the lower boundary, comma, then the upper boundary, and hit enter. And so the area under the curve is 0.866, or we have 86% of the area between negative 1.5 and 1.5. Let's try this one. Find the area under the curve for the z value to the left of z equals 1.36. Well, to the left of, what does that mean? We'll start by plotting 1.36, and we want all the area to the left of that. So on your calculator, second VARS distribution, go down to normal CDF, and the lower boundary this time, you need to write like negative 10. The lower boundary of negative 10, the upper boundary of 1.36. Now, negative 10 is because we're coming from the left and going all the way up to 1.36. So negative 10, you could also put in negative 100. You could probably put in negative 9, just negative a big number so that it knows we're coming all the way from the left. And hit enter, and you get the area under the curve is 0.913. Now, those of you with newer calculators might see an automatic input of negative 1 e to the 99 as your lower boundary. And that's just their way of saying it's a really, really, really big negative number. So you can leave that there if you'd like to, or you can put in negative 10. Either way is fine. Find the area under the curve for the z value to the left of z equals negative 2.75. Now this one's on the other side of the mean. Doesn't cover much area to the left of it. So let's see how much of the area we have. Same thing. Second VARS distribution, normal CDF. We've got our negative 10 for the lower boundary, which means we're coming from way left. And so we get an area of 0.003, very small. What happens if we need to find the area to the right of negative 2.75? We need to switch our bounds. So now our lower bound is going to be negative 2.75, and the upper boundary is going to be 10 because we're coming way from the right. So this time, if we plug all that in, we get an area of 0.997. There we go. There's your introduction into continuous distributions and area using the king of statistics, our fellow Z. Next time, we're going to go a little bit deeper and look at probability.